Hello and welcome to our continuing ongoing lectures on vector fields. So now last time I had introduced this notion of F related vector fields where F is a smooth map. Now let's so here is looking at the inclusion map of a submanifold in a manifold M. So the first thing is let Y be any vector field on the big manifold. Now what does it mean to say that Y is I related to something on S? It just means that, as it turns out, then Y is I related to X. Oops, perhaps I should start the next page. Then Y is I related to X for some X if and only if and only if Y at the point P, so here's the big manifold M and the submanifold S. So Y is a bunch of arrows. So P is a point on S. So I would like this Y to be tangent to S at P if and only if YP belongs to TPS for all P in S. So this is an if and only if statement. So one way is that suppose this condition holds that YP is tangent to TPS for all P in S. Then we can define if YP belongs to TPS, you can define a vector field, let XP equal to just YP. Then it's from what we have said already regarding smoothness of maps and so on, are restricted to submanifolds. Then this construction, just restricting it to a submanifold, then X is a smooth vector field on S. The point is that this to say that something is a smooth vector field on S, I need the condition that whatever I'm going to define should be in the tangent space of S, not the tangent space of M. And I'm assuming that condition already here. YP belongs to TPS. I'm just calling it a different name. So I could have very well said that let X equal to Y restricted to S. That's fine as well. So I get a vector field, and now this is almost trivially I related to. So because what I want to check is DIP XP now the derivative of the inclusion map is just the inclusion map on the level of tangent spaces. So in other words, it is like identity except that it's not the same space, it's a subspace. So DIP of XP is just XP itself, but XP is the same as YP, and this is Y I can write as Y at IP. So the way I've written it, it's I've set it up so that the I related condition is holds. So this equal to this, that's the I related condition. And this equation, well, it also tells us that conversely, suppose I have Right. What would be the converse? It would be that if y is related to I related to some x, then y is tangent. So suppose y is I related to converse. If y is I related to x, which is tangent to the submanifold, then we again look at this condition, that I related condition which I have written here. What does it tell us? Well, the leftmost side has to be equal to the rightmost side. But again, the leftmost side is equal to this because the derivative of inclusion is the inclusion at the level of tangent space. So this is xp. So everything whatever I've written here continues to hold, and that's xp, and that should be equal to yip, which is the same as yp. It's just that the order in which I write the equalities will get switched around a bit. So I'll end up getting the same thing. D rather that xp would actually be equal to yp. So in particular, therefore yp would be tangent to this. These are all trivial statements that I'm making here, just going through the definitions. But what would be more interesting is if another question one can ask is, question so given x in S, does there exist y in the big manifold which is I related to x? So as we have seen, I related to x just amounts to saying that the restriction of y to the submanifold is x. Now, so what we are asking is, given a vector field on the submanifold, can we extend it to a vector field on the big manifold? And it turns out the answer is yes, but we need an ingredient which I haven't discussed yet, so I won't prove it right now, but I'll just state it. Answer. Proof uses what are called partitions of unity, which are sort of basically we have seen the use of these cutoff functions, C infinity functions with compact support. We have used it often. This is something one starts with such things and then builds up some other object, which enables us to, the main use of such a partition of unity is whenever things are defined locally, if you want to define it on the whole manifold, you sort of patch up the local things and get it. Here, for instance, locally it is always possible to extend a vector field. So if I have a submanifold and let's say this x is here, I can always extend x to a locally to something y. And the reason I can do this is I just use a slice chart, and in the slice chart I sort of you make define y to be such that it's sort of constant along the it's basically x. Y should be x along all the horizontal slices. Roughly that's the idea, but we won't be needing this extension, so I won't prove this. Now another important sort of example is the following. If in general, let's see an extreme case, there may not be any y in the target manifold which is f related to x in M. So the setup is the same. So f from M to N, there's an x here, and we are looking for a y. So given x, there may not be anything in there may not be a y in the target which is f related to x. And here's an example. So let's look at the map from minus pi to pi, the interval to R2, f of t is sine 2t, and then sine t. So this is a curve which looks like figure 8. So t is 0, it is 0, it starts at the origin. As t increases, it will stay in the, it will go like this. Well, my drawing skills are not that great, so I have to do it again. So it will go like this. Let me put an arrow here to indicate that. So here, this is as t goes to pi, I'll move along this arrow. Now, as t, this is t equals 0. So as t becomes negative, it starts going down, and again it comes back to this. So this corresponds to t greater than 0. This is t less than 0. Right. So so I want to say that this, let's start. So my domain manifold is just an interval. Target manifold is R2. So on the domain manifold, let's take the vector field. Let xt equal to, I just take the, on any open interval, there's a natural vector field, namely the standard derivative operator d by dt at the point, so let's call it t naught at t equals t naught for all t naught in minus pi to pi. I take this, which is actually just the standard basis for the tangent space at each point. Now, what does it mean to say that something is f related? So I need to just, let's look at dft of xt equals dft of d by dt. This is what we called, this was our definition of f prime t. So maybe I should put t naught just to be clear. So let me put t equals t naught here. So this will be t naught. So, and we know that this, in the case of regarding, I mean, if you regard f as a curve in R2, this notion of derivative coincides with our usual notion of derivative, where we just differentiate this component wise, this curve. So that will give us 2 cos 2t naught sine of that's cos of t naught. This looks a bit hard to read, so let me just rewrite this whole thing again. So this is 2 cos 2 t naught cos t naught. And this is supposed to be if there is a y in a vector field on R2 which is f related to x, then this df t naught of x at t naught should give me y at f of t naught. Then df t naught at x t naught should be y by definition of f related. So this is f of t naught, and this is actually, so we have seen that the left hand side is actually equal to this thing here. So I won't write it again. So the left hand side is this 2 cos t naught and then cos t naught. But notice one thing that, let's now take t naught to be, so all this stuff was done for any t naught. Now let's just take t naught to be 0. So in which case take t naught equal to 0, and then what one would get is y of 0, f of t naught would also be 0. So, and here I'll get, by plugging it in this formula here, I'll get, so cos 2 pi, so this is 2 comma 1. Y naught would be this vector. On the other hand, the same point f of t naught as this origin is also the limit of f of t, since f of t, limit of f of t as t goes to pi is also equal to f of t naught, f of 0 equal to 0, comma 0. Well, instead of writing 0, comma 0, I'll just write a single 0. The origin. So since this holds by continuity of y, after all y is supposed to be a smooth vector field on R2, so it certainly is continuous. This would imply that limit t going to pi of limit t going to pi of y of f of t would be equal to y at 0, which we have seen as 2 comma 1. But now arises the problem. So we already know that what y at f of t is given by dft at x t naught, and this is basically a cos 2. So the left hand side is limit t going to pi 2 cos 2 t naught 2t cos t. As t goes to pi, this goes to the first term is okay, but the second one is minus 1. So this would be 2 comma minus 1, but it should also equal to 2 comma 1, which is impossible. Now geometrically it's clear enough. After all, this equation shows that dft xt is the same thing as the tangent vector to this curve at this point. So since the curve is going like this, the tangent vector should point like this. This is the vector 2, 1. On the other hand, the same point is being approached by the curve again from this side. So the tangent vectors to this portion of the curve will point in this direction. But the tangent vector to this curve is precisely the f-related condition tells us that the tangent vector to this curve is precisely y at that point, if a y existed. So at this problematic point, the origin, y would have to assume at least two different values. In fact, if we go along to minus pi, we'll get another one. So y cannot be, so y does not exist, in short, which is f related to x. All right, so that proves that in general it may not be possible to find f related vector fields. Now I want to talk a bit about, now that I've introduced this notion of f related, let me just mention one more thing. It's just a restatement of something that we already know, namely a vector field on a Lie group x on a Lie group G is left invariant if and only if it is LG related to itself for all G in G. So this is just a restatement of something that we have already seen. This is in fact the definition of a left invariant vector field. So because what does this mean actually? So LG, as we know, is a map from G to G, left translation, and it's a diffeomorphism in fact, but we don't need that. To say that X is LG related to itself just means that dLG at any point P, X at P should be equal to X at LG at P. So since I said it's related to itself, X is making an appearance on the right side as well. Normally it would be Y, but and then LG of P is just, by definition, it's just GP. So in short, the LG related condition is precisely the left invariance condition. A slight, we had defined LG left invariant by using the identity, but we had seen way back that can use any point. So LG related is the same thing as this left invariance, and conversely left invariance gives us this property, that this equation, and that is the same as LG related. So it's just a restatement of what we have seen before. Now before moving on from the topic of vector fields, there is a fundamental construction operation involving vector fields which I would like to discuss for a bit. So this is called the Lie bracket of vector fields. So this is an operation where the input is two vector fields and using two vector fields, we are going to get one more vector field out of that. So this is denoted by x square brackets y. So this is a map. So this map is a function from vector fields on M cross vector fields on M back to vector fields on M. It's defined as follows. So I want to say what the Lie bracket of xy. So this is supposed to be another vector field. So let's take a point. Let P belong to M. And this thing, if I specify what it is at P, then I'm done. So, and to say what it is at P, I have to regard it as a derivation at P. So let's see what its action is on a C infinity function. So this value at P acting on F, we define it to be, this is the definition. Well, it is xp yf minus yp xf. Now here what we have to note is that yf, when I write this yf, this is actually, so f is a C infinity function on M, y is a vector field on M. The combination can be regarded as a function on M, which I've, in fact, we use this function to talk about smoothness of y. So this function, this is a function on M. Its value at a point x is yx at f. This is something that we had seen earlier. And same thing with xf as well. So these two are functions, and then again one is doing the, so it's like you're taking mixed partial derivatives. So if we think of y acting on f as taking a directional derivative, then x acting on that is taking one more derivative. So it's like a mixed directional derivative, and this is also, but somehow the fact that we have changed the order of differentiation will end up giving us something non-trivial in general. So in fact, I have a few things to say about when this will be 0 and so on. But in general, this may not be 0. And the other thing I wanted to say was that, right. So this is how it is defined. But there are things to check. One is that first and foremost, even before talking about smoothness, one has to check that this thing here on the right side is in fact a derivation. Is a derivation at P. Once I know that it's a derivation, so I get so I have a tangent vector. So in other words, this gives me a tangent vector. As of now, it's just something starting with a smooth function. I've obtained a real number. But actually what I want to claim is that this acts like a derivation. So I have to check Leibniz rule and linearity. So I'll do that and then say a few words about smoothness in my next lecture. So thanks.